There we go. And the idea of this talk is, I think, to compile what we have learned along with my team a little bit everywhere, at EPFL, at ETH now, and some of the work that we will continue doing at Berkeley on carboaluminates, on these AFM phases that have this notorious role to play in LC3 cements, although they are not particular to LC3 cements. And why do I think that after all these studies and all these years studying these phases, this is actually the key to the high performance that we observe in this ternary blended cement. So LC3 is, or CEM1T if you want in ASTM C595 jargon, is a combination of clinker, calcined clays, limestone, and gypsum. This is the recipe that you are all kind of familiar with, what we call the LC350 2-to-1 in project jargon, but reality is that this is really a family of blended cements that combine these three main components, and the proportions can vary depending on the kind of performance that you want to get, the early strength that you're willing to get, and the amount and grade of the calcined clay that you are going to use. And among the advantages of this cement is that we have, well, 50% clinker, are actually less. Some of the work that we are doing right now is to look what happens and how further down below 50% we can go with the clinker content. And we can save between 30 to 40% of the CO2 by doing so, depending on the technology that you use to calcine the clay, because that's, of course, not a carbon neutral process on its own. The magic of the process is that we use this material called calcined clay, and the reactive component inside calcined clay, or at least the most common and most reactive of them, is metakaolin. That's a metastable amorphous aluminosilicate, and by calcination we obtain it basically by removing structural water from kaolinite, which is a crystalline material that occurs in nature, and forming this phase which is amorphous and that we call metakaolin. And the advantage is metakaolin is that it's very reactive. It's, I would say, the most reactive SCM that we have at scale, let's say, to be used in cement, and it's also very abundant, so the resources are very high. And this is not anymore a lab scale experiment, and I just included here a picture of a trial placing of LC3 concrete in California by National Cement a couple of months ago. So this is also happening in other places in the country, and this is a reality. We're in the process of scaling up this technology throughout the country, and I can attest that this is also the case in other regions of the world. So replacing part of the cement, which is equivalent to, say, reducing the clinker factor, is the most effective way that we have to tackle the CO2 problem of the concrete industry, at least fast, on a short time scale. And why do we go for limestone and calcined clays? Because they are very abundant as compared to the demand of cement that we are right now. None of the other SCMs, even combined, can reach quantities and availabilities that can compare, for example, with a 50% replacement of that quantity of cement. And you need to imagine that these are figures from 2016, this is dynamic, and the demand of cement is actually growing, and is growing not in the developed world, not in the global north, but actually in the global south. And the second reason to use calcined clay is because they are just reactive. They are much more reactive than other SCMs. Calcined clays are here. This is the heat release that we obtained by the ASTM C1897 method, or R3 test. And you can see that they're significantly, on average, this is more than 100 materials that we tried, than natural pozzolan, fly ashes, and even slag. And why reactivity is so important? Because reactivity pays off in clinker savings, and this is what we are trying to achieve from a CO2 saving point of view. And what we are trying to do here is a comparison between calcined clays with raw volcanic natural pozzolans. And what we took was the Chilean market as an example, because this is a market where you only find pozzolanic cements with volcanic ashes. And we took the two grades of commercial cement. These are not cements that we blend in the lab, but these are actually commercial products, with 80% clinker factor for high strength and 65% clinker factor for general use. And we compared them with LC3 type formulations. And what we did was to vary the clinker content to try to match the requirements of the standard in Chile with something that contains calcined clay. And what we found is that in order to match what the standard prescribes for high strength, remember 80% clinker factor, when you do that with natural pozzolans, you only need 35% clinker if you do it with calcined clay. Why? Because the calcined clays are more reactive. And if you only need the general use performance, actually you only need 25% clinker factor in that material. So in essence, what we demonstrate in this study is that you can save between 40 to 45% clinker when you use calcined clays. I would say not really LC3, but calcined clay as compared to natural pozzolanic, just in the difference of reactivity. But then the question is, what makes these pozzolans, which are calcined clays, so special? What separates them from the other pozzolans that we have out there? And in order to understand that further, we need to have a look at reactivity. And I really like that Craig had a little bit of an introduction to Cement Chemistry 101 in the session in the morning, so we don't need to go over this into too much detail. But I just compiled here the pozzolanic processes that are involved in LC3 reactivity. And to me, I think that we need to move to a more general, modern definition of pozzolanic reaction to any reaction that consumes calcium hydroxide. And as we will see here, not all of those reactions lead to CSH. Some of them do, but we have other processes involved as well. So the classical one is the typical suspect, where we have metakaolin reacting with calcium hydroxide to form cash, and therefore reducing porosity and increasing our performance. But in type 1L cements, and this is what makes carboaluminates not exclusive to LC3, we have a reaction between the alumina from C3A in type 1L and the calcium carbonate and some calcium hydroxide to form hemi and monocarboaluminates, which are our carboaluminates as a group. These belong to the AFM family of phases, and what's happening here is that, in essence, when you have carbonate in the system, the thermodynamic stability moves from monosulfate, which is what would form in a normal cement, to mono and hemi-carboaluminate. In reality, at least in Europe, there is no more OPC without at least 5% calcium carbonate, because I don't know if you're aware, but producers in Europe are allowed to put up to 5% calcite without declaring it. So in a sense, monosulfate is a myth of the past, and the AFM phase that you find in all cements nowadays is hemi and monocarboaluminate, because you have that carbonate component in the system. The interesting thing is when you have an additional source of alumina, in this case the calcined clay, because here the alumina from the calcined clay can actually react further with the calcium carbonate to form more hemi and monocarboaluminate. And this is why we hear these phases mentioned surrounding LC3, because we actually form more of them in this system, because we have so much alumina available by providing calcined clay. But this would be also the case if you use fly ash or other SCMs that contain alumina. It's just that the process is going to be slower because you're limited by the dissolution rate of your SCM. What's cool of these phases, which are crystalline, by the way, and with this I want to mark on the point in the morning that you need an amorphous material in order to increase performance. No, what you need is to fill space and decrease porosity. AFM is a crystalline phase. We can actually see it by XRD, and this is how we quantify it. And from a microstructural point of view, these phases precipitate, is in red here, in the large pores, capillary pores, that are left behind after clinker hydration. And if we look even closer, what we see is that these AFM phases, these crystals of AFM, integrate between these CSH and other aluminate hydrates, creating something that is uniform and reduces porosity and provides mechanical performance consistently in our material. We went even further in trying to understand this process, and we were actually able to identify a kinetic feature that we observe in the calorimetry curves of LC3 cements that relates to the precipitation of hemi and monocarboaluminate. So you remember that we say hemi and monocarboaluminate occur in every cement that contains carbonate, but we have more in LC3. And something that we observe in LC3 cements is this hump here. We also observe it in OPC, but in LC3 it's bigger. So we were wondering, well, what is that? And by comparing the heat release on this third peak of baptized third peak of hydration, if we count as first the halide dissolution, right? Not the dissolution peak that is before. We start from here, 1, H2, 2, third peak of hydration here. When we compare the heat release over that peak, it correlates very well with the amount of carboaluminate that we can quantify by X-ray diffraction. So basically now we can assign a feature that we can observe in the calorimetry curves of an LC3 cement with the precipitation of hemi and monocarboaluminate. And we can start seeing some particularities of the process. So first of all, this doesn't happen in the first 24 hours. So whoever is thinking that what we need to do in order to improve the early age strength or the 24-hour strength of LC3 is to increase the reactivity of calcined clay, you're looking in the wrong place because the reactivity of the calcined clay is coming after that. Before that is the clinker. It's happening after 1 day, between 2 and 3 days actually, and the position of the peak changes as a function of the metakaolin content that we have in the system. And this is very interesting because this is exactly the same period of time when we see that the porosity of LC3 plunges, and we have this refinement, as people like to call it, of the microstructure where we go to these very, very, very small critical entry radius that we can measure by MIP. But in a sense, we still have a disconnection between kinetic features that we can observe by calorimetry or XRD and the mechanical world, which is more related to porosity. And I think that the ultimate confirmation came by comparing calorimetry with in situ ultrasound pulse velocity, which is related to the elastic modulus. And as you know, elastic modulus evolution is directly correlated with development of compressive strength. We actually have an equation in 318 to relate the two things. And what we observe is that since the precipitation of carboaluminates in calorimetry, we know that it's related with the metakaolin content, well, we see the same kind of decoupling in the mechanical signal. And now we can associate a kinetic feature, a heat release, that we know that corresponds to a chemical reaction with mechanical consequences of that precipitation. So carboaluminates do contribute to strength. And actually, they explain how a cement with 50% clinker can catch up the strength of a type 1-2 between 3 and 7 days. And why between 3 and 7 days? Because you have to wait for this to happen. This basically closes the loop of how LC3 works, in a sense. Oh. So, what's interesting, though, is that we start seeing some disagreements between what we observe experimentally, which is always a mixture of hemi and monocarboaluminate, and what thermodynamic models tell us. So for an LC3 type of system, thermodynamically, only we should be observing monocarboaluminate. And irrespective of the degree of reaction of metakaolin, right? So you can be at any point of this line, which is degree of reaction of metakaolin, and the only AFM phase that you're going to observe is monocarboaluminate. And the reason for that is that in the database, the monocarboaluminate that was used to obtain the thermodynamic data is pure or synthetic monocarboaluminate. And we went a little bit deeper to try to see if that was the case of the phase that we actually have in LC3 cement, and we did that by producing synthetic carboaluminates from hydration of pure C3A, and we added certain amounts of gypsum to the system. And what we see is that the more gypsum you add, you start forming monosulfate in combination with carboaluminates, but not always. And this is the interesting part. If you are only 3% sulfate, we still see only carboaluminates. We do not see the line for monosulfate, which is here. And we use Raman actually to observe and confirm that there is sulfate being incorporated in the lattice of hemicarboaluminates, and we believe that this is the reason why in real LC3 systems, hemicarboaluminate exhibits long-term stability, which is something that we do not see in the database that we have right now. So basically that's a reason to update the database. We probably need more data to do that. But that's the mechanism and the explanation that we have so far. So in essence, we don't have pure monocarboaluminate, but rather a solid solution between, well, pure hemicarboaluminate would be hydroxyl and carbonate. That's the hemi part. The other hemi is hydroxyl. this will have sulfate a little bit as well in the lattice. But in a sense, and overall, even in the long term, these AFM phases continue to precipitate in the microstructure of LC3. This is an overview of what happens at 3 years. We have some conversion of hemi-carboaluminate into monocarbonate in the long term, but what I want to highlight here is that hemi-carboaluminate is observed in the microstructure even in the long term. So this is a phase that has thermodynamic stability in the long run. And of course, in the high alumina system, we also start seeing this phase which is called Stradlingite, which is a silicon-based AFM phase. Doesn't really matter because they precipitate in the same manner, and at the end of the day, as we were saying at the beginning, the goal is to reduce porosity and fill space. So what are implications of this carboaluminate precipitation for the horizons of LC3? For example, if we try to go below 50% clinker factor. So the problem with going below 50% clinker factor is that you have to remember that calcined clays are very reactive, but they are still pozzolans. So if you mix calcined clay with water, you get mud, expensive one. We need lime, we need calcium hydroxide, reactive calcium to get this process going. And if you reduce the clinker factor too much, what happens is that you run out of calcium hydroxide very quickly in the process. Idea, what happens if we add calcium hydroxide on top of this as a doping agent? This doesn't make any sense from an environmental point of view, but from a chemistry point of view, what happens if we do that? So then we push the calcium hydroxide content up, and the advantage of doing that is that then we can sustain the metakaolin pozzolanic reaction even with clinker contents of as low as 15%. And why do we want to sustain the pozzolanic reaction in this low clinker LC3s? Because sustaining it means that we keep precipitating these key phases, carboaluminates, in order to fill these big capillary pores that we have in the microstructure and therefore increase the strength. So if this all connects, we would expect to see an effect of these calcium hydroxide additions in the compressive strength, right? Well, in LC350, we do not see effect because in LC350, that's a system that is not limited by lime availability, at least not when kinetics are considered. But as we start going down in clinker content, you can see that the purple bars, which are the systems that are doped with calcium hydroxide, we get significantly higher strength than the reference system. And in the case of LC315, we basically get double. And that doubling of strength compared to the control is coming from the carboaluminates. Like the system without the calcium hydroxide doesn't have the carboaluminates, the other one does. And this is more than irrefutable proof that these phases are contributing, as CSH and everybody else, to compressive strength. But of course, and this is what I was trying to say at the beginning, please don't take away home that this is a good idea from an environmental point of view, because actually, if we decarbonate limestone to produce calcium hydroxide, the CO2 footprint is actually higher than Portland cement, so it would be better to keep the clinker factor higher. But from a chemical point of view, I think that is a nice perspective, because if we find a way to produce calcium hydroxide or hydraulic lime in a cleaner way, or if we manage to design a process where we can fully capture that CO2 and utilize it somewhere else, well, then maybe one day this could make any sense, but certainly not decarbonizing calcite to do it. So with that, I would like to move to my conclusion. So LC3 cements decrease their porosity considerably between 48 to 72 hours. Again, this is the time period where the strength catches up with type 1,2. And now we know that the reason for this decrease in porosity is associated with the precipitation of carboaluminates. From a kinetic standpoint, this precipitation can be associated with this third peak of hydration, which I think is really nice, because if we just want to study when this precipitation is happening, basically we don't really need to do XRD. You can just look at the calorimetry curve, and wherever this third peak of hydration is will tell you when do you have your enhancement of carboaluminate precipitation. From a thermodynamic point of view, I think that it's interesting that we observe incorporation of sulfate in the lattice of hemicarbonate. And that's a pathway for further work, because certainly we need to update the solid solution models for that phase in our databases. And in low clinker LC3, what I mean 50% is already low clinker, like that's much better than what we have in the market now. But with low here, I mean less than 50% clinker, the contribution of carboaluminate precipitation to strength development is even higher than at classical 1T 50% clinker cements. So with that, I would like to conclude. Thank you for your attention, and happy to take any questions.